Welcome to the Deep Dive, the show where we take a complicated stack of research, notes, and articles, and we decode it so you can jump right to the core of the knowledge you need.
Today, we are wading deep into one of the most persistent and, frankly, hidden challenges in modern cybersecurity, the world of stripped binary code.
This sounds dense.
It is. This isn't just complex. It's the ultimate maze that security analysts navigate every single day. And it's also the perfect hiding place for cybercriminals.
Okay, let's unpack this right away because this feels foundational to securing pretty much any modern software. So when a developer writes code, they use all these human-readable labels, right? Variable names like customer-id, function names like calculate-tax.
And, crucially, comments explaining the really tricky parts. But the second that software gets compiled into an executable program, all that beautiful human context is, well, it's intentionally shredded.
Intentionally? What?
It's all about optimization. The compiler's job is to create the fastest, smallest set of raw machine instructions it possibly can. Explanations, high-level names, that's all just extra weight to the machine, so it strips it all away.
And this process is what you'd call lossy, I guess. The information is gone for good.
Exactly. Irrevocably lossy. The result is this cryptic sequence of ones and zeros. It's perfect for a computer, but for a human trying to reverse engineer it, it's a nightmare.
One of our sources gave a fantastic analogy for this. Imagine you're handed an organizational chart for a huge company, and your job is to figure out who does what.
Right. You can see the structure, you can see the box A connects to box C, and that triggers something in box F. The flow is there.
But the purpose is completely gone because instead of those boxes being labeled HR department or finance, they're just called Group A, Process B, and Task X.
You see the traffic, but you have no idea what it means. And for analysts, that's the whole problem. They can't tell if Task X is benign, like processing a payroll, or if it's malware hiding in plain sight.
So, our mission for this deep dive is to explore the breakthroughs designed to restore that lost context. We've got sources detailing a really cutting-edge AI-powered tool called ReSym, developed by researchers at Purdue.
ReSym is essentially an intelligent decoder for this binary world. It uses large language models, LLMs, to look at that cryptic sequence, analyze the structure that's left, and then it reconstructs the missing pieces.
The variable names, the function labels, the things the compiler threw away.
Exactly. It's trying to restore the developer's original intent.
And this isn't just some academic theory. ReSym actually won the prestigious ACM CCS Distinguished Paper Award. So the top minds in the field are saying, hey, this is a big deal.
A very big deal. We'll definitely unpack how ReSym works, especially how it succeeds where more general LLMs tend to fail. But we also need to zoom out and look at the whole landscape here.
Right, because ReSym isn't the only game in town. We'll be looking at how it compares to two other major approaches. A highly specialized neural network tool called DIRTY.
And a really interesting probabilistic technique called Osprey. They all tackle the same problem, but from very different philosophical angles.
Okay, so ReSym's big claim is that it can automate a process that, until now, has been incredibly manual and slow. So let's start there. Let's really establish the depth of the challenge these tools are up against.
To do that, we have to understand just how destructive that compilation process really is to readability. It's more than just optimization. It's a process of translation and, compression.
It's taking a high-level idea, like a C structure, and squashing it down into raw assembly instructions that manage memory directly.
And to do that efficiently, it throws away everything that doesn't map directly to a machine instruction. So your comments, your variable names, your custom type names, even the whole concept of a class or an object.
All gone.
Completely gone. So when an analyst comes along, they use a tool called a decompiler, something like ID Pro or Ghidra. These are essential tools, but they have fundamental limits.
What can they do well?
They're great at reconstructing the structural properties. They can see the boundaries of a function, they can map out the loops, the control flow, they can show you the basic architecture.
So they can tell you that a block of code exists and how it connects to another block.
But not why it exists exactly. When it comes to the crucial semantic elements, the descriptive names, the complex user-defined data types, a deterministic recovery is technically impossible.
Why impossible?
Because there could be multiple different source codes that, when compiled, produce the exact same binary. The decompiler has no way to know which one was the original. It can't just guess a name or a type with any certainty.
Okay, so let's make this concrete. Our sources had a couple of really good examples of this semantic loss. The first one was about custom data types.
Right. Think about a programmer working on, say, a graphics application. They might define a custom structure, let's call it PNTT, to hold X and Y coordinates. Internally, it has two floating point numbers named very clearly X and Y.
Super clear in the source code. But then it gets compiled. What does the decompiler show the analyst?
Well, the semantic meaning is just gone. The decompiler only sees two memory locations next to each other being accessed. It might translate that back into some generic C code where the accesses look like array indices, something like A0 and A1.
So the analyst sees a generic two-element array. They lose the fact that it represents Cartesian coordinates and, maybe more importantly, they have no idea if A0 is X and A1 is Y or the other way around.
Exactly. The high-level intent, which took the developer seconds to write, could now take an analyst hours or even days to piece back together. And that's a simple case.
It gets worse with data layout and this thing called padding.
Oh, yeah. This really throws a wrench in the works. Compilers love memory alignment. For performance, they want variables to start at memory addresses that are multiples of, say, 4 or 8 bytes.
It's like putting little spacers on a shelf to make sure everything lines up neatly, even if the items themselves don't perfectly fill the space.
That is a perfect analogy. The compiler inserts these digital spacers padding bytes. So if a developer has a 3-byte character array, the compiler might stick 1 byte of padding right after it for alignment. The decompiler just sees 4 bytes of space.
And it can't tell the difference between the meaningful data and the padding?
Nope. It has no way to know that one of those bytes is just junk. So it might misidentify the whole thing as a generic 4-byte array, assuming all 4 bytes are meaningful data.
And that's a critical structural error, right? It's not just a naming problem anymore.
It's a fundamental flaw in the recovered structure. It messes up any further analysis downstream because the memory layout the decompiler thinks it's seeing is just wrong.
And the stakes here are just enormous. This isn't just some academic puzzle. Our sources say cybercrime costs are projected to hit $10.5 trillion annually by 2025.
That number is just staggering. And it really underscores why automating this is so critical. We have to secure our infrastructure, our software supply chains. And security analysts just can't keep up doing this manually with tools that are, maybe 37% accurate on a good day.
We need tools that can look at that box labeled Task X and say, with high confidence, that's almost certainly the network packet handler.
And that brings us right to ReSym.
Right, the AI breakthrough. ReSym is pitched as the answer to this slow, manual, error-prone process. It's ambitious because it's going straight for the most human part of the code, the meaning, the semantics, the names. So how did the Purdue team get an LLM to work on a problem that general LLMs, like GPT-4, have really struggled with?
Okay, so ReSym is fundamentally an AI tool built to reconstruct that missing information by finding patterns in the software structure. And LLMs are great at that, but and this is the key, it operates with a very specific set of constraints.
So it's not just reading the raw text of the decompiled code.
No, not at all. It infers the likely meaning by comparing the structural fingerprint of a function against the millions of examples it was trained on. It's looking for those patterns of use.
So it's essentially restoring the human intent. Instead of an analyst spending days figuring out that V1 is probably the customer name buffer, ReSym just suggests that name automatically.
And with high confidence, it completely changes the analyst's workflow. One of the researchers, Lynn Tan, framed it as essential for malware analysis, vulnerability detection, and securing critical infrastructure. The emphasis is on automation.
And that specialization seems to be the key. The sources were clear that you can't just take a general-purpose LLM trained on, Wikipedia and Reddit and expect it to work here.
Exactly. When they tested them, general LLMs completely failed to provide useful information about the complex data types that developers create. They just couldn't handle it.
So why does a massive general LLM fall flat on its face with this?
Because decompiled code is not natural language. It's not even natural code. It's full of noise, strange artifacts, and logical gaps left by the compiler. It takes a human years of specialized training to learn to read it.
So ReSym had to be specialized for this noisy environment. How did they do that? What exactly does it feed the model?
It's not just the raw text. ReSym feeds the LLM what you could call contextual metadata. Things like where a variable is stored, is it on the stack, the heap, is it global? It looks at the specific instructions that access it, the data flow graph of the whole function.
So it's like giving the LLM the cryptic text, but also attaching a bunch of footnotes that say, warning, this memory access is definitely a loop counter, or hint, this variable only ever gets passed to a function that prints things.
That's a great way to put it. It uses these structural properties as a strong steering mechanism. For example, if a variable is only used to count a loop and then gets passed as an argument to a library call that needs an array size, ReSym's specialized model is way more likely to infer the name array size or loop count.
Whereas a general LLM would just see it as V5 and have no real context.
Precisely. And this shift from manual work to automated specialized suggestion is huge for security. Let's talk about the specific applications.
Okay, let's start with the big one, cybersecurity.
For malware analysis, this is a complete game changer. Malware is almost always stripped and obfuscated to make it hard to analyze. By giving meaningful names back to the functions and variables, ReSym lets an analyst quickly understand the malware's logic.
You can see the command and control structure, how it hides itself.
Right, it compresses weeks of manual work down into minutes of AI inference time.
And what about legacy code? That's a huge problem in industries like defense and finance.
Absolutely. Think about critical systems that have been running for decades. The original source code is lost, the original developers are long gone, and now there's a vulnerability. Engineers are stuck analyzing a stripped binary to figure out how to patch it.
ReSym could help them make sense of that code base quickly.
Exactly. It allows for crucial maintenance and patches without having to do a full manual rewrite from scratch.
And the last one was intellectual property protection. How does that fit in?
Well, if a company needs to prove that someone made unauthorized changes to their software, maybe a competitor bypassed a license check or stole an algorithm, ReSym helps decode the structure to identify exactly where and how those modifications were made.
So it's valuable across defense, aerospace, healthcare, any industry that needs to control its software assets.
And that real-world utility is why it got that big award. But it's also important to see that ReSym, as cool as it is standing on the shoulders of earlier machine learning research that was focused more on type recovery.
Right. To really get the whole picture, we need to look at the evolution here, and that brings us to a tool called DIRTY.
Exactly. To understand this lineage, we have to talk about DIRTY. It stands for Decompiled Variable Retyper. This project focused heavily on recovering not just the names, but the detailed, complex variable types.
So it was tackling the structural problem first.
It was. It showed how specialized neural networks could attack this problem before LLMs really started to dominate everything.
And DIRTY's goals were ambitious. It wasn't just renaming V1 to index. It wanted to provide the semantic type, like the actual structure name, maybe user config, and also the syntactic type, the memory layout, the field offsets.
And it did this at scale. It supported a library of over 48,000 possible types that were found in the wild. That's way beyond what older rule-based systems could ever handle. It showed that machine learning could really scale this problem up.
Let's talk architecture, because this is where DIRTY made a leap that, kind of foreshadowed what ReSym would do. It used a transformer-based model.
And using transformers was a huge innovation in the binary analysis space. It was a move away from older models like LSTMs. The reason is that transformers are just fundamentally better at capturing long-range dependencies.
Okay, what does that mean in the context of code?
Well, in a program, a variable might be declared on line 1 of a 100-line function, but the best clue to its real type might not show up until line 75 when it's used in a very specific way.
And an older model, reading line by line, might forget the context from the beginning.
Exactly. A transformer, though, can effectively look at all the uses of that variable simultaneously. It understands the variable in its entire context, no matter how far apart the declaration and the use are.
And they trained it on a huge data set, right?
Massive for the time. It was trained on a public data set called DRT, with nearly 1 million unique functions from GitHub. This huge corpus allowed the model to learn all the idiomatic ways that real developers write code and structure data.
Okay, now for the really clever part. The data layout encoder. This was DIRTY's solution to that compiler padding and alignment mess we talked about earlier.
This is where it gets brilliant, because it starts from the assumption that the decompiler itself is flawed. It knows the decompiler might see a 3-byte array with padding and call it a 4-byte array. The data layout encoder is designed to correct for that.
But wait, if the decompiler's output is sometimes wrong, you can't just trust it as the absolute truth, right? The model would just learn the same mistakes.
And that is the crucial insight. It doesn't use the decompiler's information as a hard constraint. That would be too brittle. Instead, DIRTY learns a soft mask.
A soft mask? What does that do?
It basically learns the decompiler's historical failure modes. Instead of saying this type is impossible, the soft mask just reduces the probabilities of incompatible types without setting them to 0. It learns, for example, that when the decompiler outputs something that looks like a 4-byte structure, there's a pretty good chance it was actually a 3-byte structure with padding in the original source code.
So it's not guessing, it's compensating probabilistically based on the decompiler's known tendencies.
Exactly. It makes the machine learning model resilient to the flaws in the tools it depends on. It's a critical feature for any real-world system.
And the second key component was the multitask decoder, which predicted both types and names at the same time. Why do both together?
Because the researchers recognize they're totally symbiotic. Names give you clues about types, and types give you clues about names. A variable named count is almost always an integer. A variable called mutex lock is probably some kind of complex synchronization structure.
So by forcing the model to predict both at once, they leveraged that correlation.
They did. And even though the raw accuracy on any single task was a tiny bit lower than a dedicated model, the overall consistency was way higher. Getting the type right made it much more likely to get the name right, and vice versa. It gives the analyst a much more coherent and trustworthy result.
And the performance numbers were impressive. It recovered original names 66% of the time and original types almost 76% of the time.
Which is a huge jump from the 38% type recovery you'd get from a commercial tool like X-Rays. It takes you from a world of variables named V1, V2, V3 to a world where they're named user index and file descriptor. It makes the code instantly more understandable.
So we have ReSym with LLMs for semantics and Dirty with neural networks for types. But there's a third, very different approach that isn't about learning patterns at all. It's about systematically managing uncertainty.
And that is where Osprey comes into the picture. It was developed by Zhang et al., and it's a novel probabilistic technique that really contrasts with the machine learning focus of ReSym and Dirty.
It sounds like Osprey is the voice of reason here, basically saying, look, this process is inherently uncertain, so let's build a system that actually embraces and manages that uncertainty.
That's its entire philosophy. It argues that since reverse engineering is always going to give you contradictory or uncertain results, the old deterministic tools, like a standard ID or Ghidra, just don't have a way to handle that. They guess conservatively or they just fail.
So how does Osprey introduce probability into what seems like a deterministic puzzle?
It starts by introducing random variables. For every memory location the decompiler finds, it creates variables that represent the likelihood of it having various properties. What's the probability this is a structure field? What's the probability its type is an integer versus a pointer?
And then it gathers evidence to start filling in those probabilities, building a huge probability map of the entire program.
Yes, and that's where its core mechanism, binary dependence analysis, or BDA, comes in. BDA is a technique that essentially creates a comprehensive ledger of every single interaction a piece of memory has with the rest of the code.
What's in that ledger?
It tracks everything. How data flows, where pointers are pointing, how memory is accessed. Was this memory written to? Was it read from a register? Was it used in a math calculation? BDA collects all these basic facts, and each fact becomes a hint.
And each hint adds a new probabilistic constraint to the model.
Exactly. So if a memory location has 5 different hints that suggest it's part of a structure, but one weird hint suggests it's just a simple integer, the model can resolve that conflict by balancing all the probabilities. The 5 strong hints will overwhelm the one noisy one.
That sounds incredibly robust. Let's dig into the specific types of hints Osprey uses, because they sound more advanced than just simple memory access patterns.
They are. The team introduced 3 really powerful hint types. The first is the data flow hint. This comes from watching memory copies or function return values.
Give me an example of that.
Sure. If a function returns a structure, and that structure is then copied into a new piece of memory on the heap, Osprey sees that flow of data. It concludes that the source and destination memory regions are probably instances of the same complex type.
So it's looking at the movement of data to infer structural similarity.
Right. And even if compiler optimization messes with one specific data flow hint, Osprey is collecting hundreds of hints per function. The collective vote of all the other hints usually guides the calculation to the right answer.
Okay, what's the second hint type?
The points to hint. This is critical for figuring out what pointers are pointing to. If a single pointer variable is found to point to 2 different memory regions at different times, Osprey assumes those 2 regions are likely instances of the same type.
Because a programmer probably wouldn't use the same type of pointer to point at 2 completely different kinds of data structures.
Exactly. And the third one, the unified access point hint, is really specific to finding the fields inside data structures.
How does that one work?
Imagine you have two variables, user1 and user2, and they're both the same type of structure, and they both have a field inside called username. The compiled code that acts as that username field might use the exact same machine instruction, just with a different base address for user1 or user2.
Ah, so Osprey sees that the same instruction is used to access the same relative offset in two different memory blocks.
And it uses that as very strong evidence that a structure is present and that the memory being accessed is a field within that structure.
And by collecting and weighing all these hints, Osprey gets some pretty incredible accuracy numbers, right?
The results were fantastic. It achieved over 90% precision and 88% recall in overall variable recovery. Compare that to IDEA Pro at around 67% precision or Ghidra at 70%.
So we're moving from a world where an analyst might get the structure right 2/3 of the time to a machine getting it right almost 9 times out of 10. That's a huge shift.
It is. And Osprey was especially good at recovering complex variables nested structures, big arrays, which are the exact things that humans spend the most time on, and where other tools fail the most.
Okay, so we've looked at 3 world-class approaches. ReSym, with its specialized LLMs for semantic naming, Dirty, with its transformers for large-scale type recovery, and Osprey using systematic probability to manage uncertainty.
Now it's time to put them all together and see where the trade-offs are in the real world.
Let's use the Karutals benchmark to compare them head-to-head. Both Dirty and Osprey were tested on it. So first up, speed versus accuracy on just recovering the structure.
Okay, so on pure structural recovery, the machine learning approach had a slight edge. Dirty hit about 77% accuracy. Osprey was a little lower, around 72%. When the Dirty team made a simplified version, Dirty Light, that only did structural recovery, it pushed that number up to 80%.
So ML is slightly better at raw pattern recognition for structure. But what about speed? In security, that's often the deciding factor. What's the computational cost here?
And this is the major trade-off. It's stark. Dirty Light was incredibly fast. It took just 75 seconds to run its analysis on the entire Karutals benchmark.
75 seconds for the whole thing. And Osprey.
Osprey is a much, much heavier tool. It's comprehensive analysis, all that BDA and constraint solving. It takes about 10 minutes per binary.
Wow. Okay, so that's a massive difference. 75 seconds for the whole benchmark versus 10 minutes for a single file. It really dictates how you'd use them.
Absolutely. Osprey is what you'd use for a deep forensic analysis on one critical piece of malware where accuracy is everything and time is secondary. Dirty, and probably ReSym too, are the high-throughput tools you'd use to screen an entire software supply chain or analyze thousands of malware samples a day.
Okay, next question. Robustness. Modern compilers use aggressive optimizations like Nanis3 that completely restructure the code. How do these tools handle that?
This is a great test of resilience. Dirty's accuracy stayed pretty stable across the different optimization levels. The reason was that the commercial decompiler it used, Hexraze, actually undoes a lot of the low-level optimizations before Dirty even sees the code.
So the decompiler acts like a buffer, insulating Dirty from the messiest parts of the optimization.
Exactly. Osprey, on the other hand, showed incredible robustness, even though it was working with more raw data. Aggressive optimization specifically targets the behaviors Osprey uses for hints, like data flow and access patterns. But even so, its performance degradation under Nanis3 was the smallest compared to its competitors.
Why was it so resilient?
Because it aggregates so many hints. Even if optimization compromised, say, 20% of the hints, the remaining 80% were still strong enough to guide the probabilistic model to the correct solution.
So it's really not about one tool winning. It's about a collection of specialized tools for different jobs.
Absolutely. And the researchers themselves know this. The authors of Dirty actually suggested that the most exciting future work would be to combine these approaches.
How so?
To take Osprey's highly accurate structural results, that 90% precision, and feed that directly into Dirty's data layout encoder as a starting point.
Ah, so you use the robust probabilistic method to get the structure right, and then you feed that near-perfect structure into the fast pattern-matching machine learning model to fill in all the names and semantic details.
That's the powerful hybrid model. It's the next logical step, the best of both worlds.
And this brings us back to why this all matters to you, the listener. We started with this impossible-to-read organizational chart, the stripped binary.
And now we have these sophisticated AI systems that can look at a function labeled task X and say, with very high probability, this is the server socket array structure, that field is the server socket, and this variable over here should be called connection count.
It just completely changes the game. It makes it feasible to secure huge, complex software systems at a scale we never could before. The era of one person manually deciphering a 5 MB binary is ending.
It's being replaced by specialized AI that can handle the volume and complexity needed to fight back against that $10.5 trillion cybercrime figure.
Okay, let's summarize this deep dive. We've explored 3 major state-of-the-art methodologies for attacking the challenge of reverse engineering stripped binary code.
First, we focused on ReSym, the new leader using large language models. Its specialty is reconstructing the semantic identifiers, the human-readable names, by tailoring the LLM to the noisy environment of decompiled code.
Second, we looked at its predecessor in a way, Dirty, which refined the use of transformers. It introduced that clever, soft mask concept to achieve high-speed, high-accuracy recovery of variable types and names.
And finally, we detailed Osprey, the probabilistic alternative. It embraces the problem's inherent uncertainty, using advanced analysis to aggregate hints, making it the most robust tool against aggressive compiler optimizations.
And together, these tools represent a huge leap past the old deterministic methods. They work by leveraging massive code databases and accepting that recovery has to be a probabilistic exercise, not a fixed rule-based one.
Which leaves us with a really important question for you to think about. We know that these huge generalized LLMs struggle with the specific nuance of decompiled code, a skill that takes humans years to master.
Given the success of these highly focused purpose-built models like ReSym, Dirty, and Osprey, is it possible that the biggest security breakthroughs of the next decade won't come from massive general AI models that try to do everything?
But will instead come from these highly specialized, constraint-aware AI architectures, designed for one purpose: to understand and repair the deep, structural logic of software itself.
It's a compelling thought. Perhaps the future of security belongs not to the generalist giant, but to the specialized architect. Thank you for joining us for this deep dive.
Let's see you next time.